So I'm the one between you and lunch. So I'm going to try to drag this out as long as I can. So I'm on the Mahout project. I'm a PMC member, committer. I've been involved for a few years. I got involved fixing a bug in k-means that was dropping vector IDs on the floor after doing clustering. So I got hooked then. It's a fun project. It's actually coming back into life. We did a period of soul searching. I'll talk about a little bit. A little bit about me. I was at Accenture for a while, heading up their data science innovation group. Recently joined Lucidworks to do data science there, building machine learning features into the search product. You can find me online at these places. We just recorded a new podcast episode last night about bad tech interviews, so watch that space. The recent developments in this project are to make matrix math simpler. I'll go into some details about how we're doing that or why we decided to do that. But mainly we're providing a very simple DSL for matrix math. We're providing an interpreter for Apache Zeppelin so you can do your work in notebooks and share context between different backends and do plotting off the same variables. We have a flexible, so the backends are a lot more rich now. We have Flink, Apache Spark, H2O, there's a stub, and we're doing work in GPUs now too, so I'll go into that too. And then lastly, a new algorithm development framework that's modeled after scikit-learn and R. So there's a nice framework where you can make new algorithms and also ship the documentation at the same time with a PR. So this is the high-level view. Show of hands, who knows the word Mahout and for one thing, who's heard of it? Okay, and who thinks it's dead? No? All right, because I heard it's dead. But honestly, we did go through some soul searching. We restructured the project to adapt to some new stuff. These are the high-level new things in there, including native solvers on the GPU. We are working with NVIDIA on that feature now. So we have single GPU. Next priority is multi-GPU. Here's a timeline. Sorry, I can't see it very well from here, but you see a couple of years ago, we saw that MapReduce was not a really good place to do large-scale, very heavily iterative processes like we do in machine learning. There was a little bit of back and forth on what to do with that back end. Spark at the time was becoming popular, and we also were looking at things like H2O. We knew Flink would be an option, so we wanted to broaden our horizons, make it possible to write matrix math, not just with MapReduce, because I think at that time the 10.10 release was when we started deprecating all the previous MapReduce-based jobs and not accepting new submissions. A book last year about this new DSL and programming framework. I have a couple copies. If anybody would like a copy, I have them in my backpack here. Please find me right after this. We added Flink backend support last year. Late last year, Trevor Grant, new committer and now PMC member, added the interpreter for Apache Zeppelin. And just more recently, well, I'll just skip ahead. We finally just released 0.13 with the native GPU, multi-core CPU, so moving out of the JVM. So that's something we're very excited about. We are still doing some benchmarking. I have some initial results. Here's just an overview of the topics I'll be going through for the rest of the talk. Finally, then how to get involved, how to find out more. So Mahout Samsara was the name we decided. It happened to be my wife's suggestion to call it Samsara because we were in a period of death and rebirth, and this is a term from Sanskrit about that sort of a life cycle. We don't have a new logo, but I did try some SVG editing. There's the new logo for this talk. Don't use it. So here's the idea behind this DSL. If you see a new paper with some mathematics that looks like the second to the bottom line, you might not want to have to go in and translate that into, a whole paragraph of chained Spark clauses, right? You might just want to take that line and say, well, you know what? I want a matrix G that is matrix B times its own transpose minus C transpose plus chi times S sub Q cross S sub Q, and that is done. So that front end and that DSL, depending on what host you're on, what environment you're on, what the shape of B and C and anything you feed it is based on special banding or triangular shapes or sparsity versus density, the system will hand that off to a proper backend that will do the job the best it can. So that means if you're running on a Spark cluster, it may hand it off to the Spark cluster. You may not want to use Spark because after 30 nodes you get negative scaling based on a paper from last year. You may want to run it on GPUs. You may want to run it on all the cores of your CPU. You don't have to worry about that. So as a data scientist, as a machine learning engineer, you can use this as a way to prototype new algorithms, new jobs, and this is designed to look like R and MATLAB. So you could also prototype in R, prototype in MATLAB. When you want to go to production, come in here and start writing this kind of code, and it's production level at that point. So that's a common pattern that we're seeing. I've seen it on client projects and at work. Prototype something in R, then translate it to Spark for production, and that's not trivial. That requires somebody to learn Spark, to get used to things, and there is a learning curve. People can pick it up, but this is intended to bring people into writing their own machine learning stuff without having to learn too much programming. I mean, most people in this room probably like writing code, but if you don't have to learn some other paradigm, this is an attractive feature for us at least. So we think it's hopefully useful for other folks. Here's just a simple example of an on-the-fly algebraic optimization. If you wanted to calculate, that equation up at the top is A transpose times A, and then the pairwise row times its own transpose. And that's a typical thing that you would use in machine learning for co-occurrence. You're taking the dot product of where items intersect each other, and their dot product then gives you a measure of how similar they are. It's very straightforward. Without any optimization, you're going to need to run, do a full scan on A, do a transpose, do a full scan on A again, and do the matrix multiplication. So this takes that down into half by looking at A as rows and columns and partitioning the data that way. And so this is a graphical view of what that looks like. You would take the color-coded columns times the color-coded rows in order, and you start doing some very simple arithmetic. Oh. And so this partitioning is just a hint of the type of partitioning that's happening behind the scenes. The other thing that we thought was valuable would be to make it so that like I said, if you wanted to use H2O, if you wanted to use Flink, if you wanted to use the next thing that's coming down every 2 weeks, you can build a backend, make it agnostic, and then you're programming. And I'm sorry if it's small and blurry for the back. Trust me, after that long comment line, the code below it is the same on the left and the right. This is in Zeppelin Notebook. The code at the top is some boilerplate imports up to ordering. Most of the imports are the same on the left and the right, but the difference there is setting up the context for Flink on the left is just slightly different than setting up the context for Spark on the right. After that, your code will move from any backend to any other backend with no changes. So that's another advantage that we think is valuable, because when you're trying this stuff at scale and things are blowing up in Spark or blowing up in Flink, what do? You reach for another tool, and if you have to rework all your code every time you do that, that's an upfront cost that you wouldn't want to have to do. So this takes away that barrier too. So the Zeppelin notebooks, if anybody familiar with Zeppelin? Okay, so it's like Mathematica or IPython. Polyglot, you can run Scala, R, Python. You can write your own interpreter, which Trevor Grant did. There's a blog post at the bottom about how to do it. I think these slides will be available online. And then there are the documents at the bottom. Coincidentally, on the new website framework that we accidentally released last weekend, by pushing something to stage that we didn't know was there. Thank you, Trevor, for the late night fixing that. So here's what it looks like. You add an interpreter at the top. You say create. You do some setup. You tell it where some jars are, and then all of a sudden you can write this code in Zeppelin. The advantage there is between paragraphs in Zeppelin, you can share variables. You can also share contexts. You can also write to disk and pull it back out. So it's a convenient way to prototype stuff. So for instance, this might hand off to the next paragraph, which you would then use to do some plotting. And I'm sorry, I can't even see that. I think it's Spark, which you might then hand off to Spark, or then to R, or then to Python, and do some plotting. So that's the idea there, to make a nice, easy workflow for this type of work. The framework for adding stuff is based on scikit-learn and R. For instance, here you have a fitter that hands off parameters to a model, and then the model has a predict function. So it's a common API that you would expect to have, and hopefully takes away a lot of the boutique, handwritten stuff that we all do, but we know we shouldn't, right? Some more documentation at the bottom there too. So, yeah, latest solve on GPU, CPU, all the cores, and coming from NVIDIA, a new committer on the project from NVIDIA, Nikolai is writing some JCUDA bindings, so we'll be able to go directly onto the card from Java. I'm sorry for this blurry slide, but it was, at the top is your application code and shell scripts. At the next level down where you might interact is the Scala DSL, the Samsara. And then you see that the compute can branch off into a couple different places. One is in core, working directly on the host, maybe pushing to CUDA, and maybe pushing to the GPU. Or you can go through frameworks like H2O, Spark, Flink, and do sort of the same pipeline. All that stuff below the DSL, you don't need to be worried about. It is handled by the system. Some benchmarking we did. We'd like to do some more, but we got some promising results with, I think, 1,000 by 1,000 random matrix multiplication, 30 times speed up with the GPU over in core. So we're going to do some bigger benchmarking. And this was just a last minute thing that Andy Palumbo did before the NVIDIA conference last week. But this is promising, and we're sure that GPUs are going to be a promising way to go, especially multi-node. This is those same results in not in a console. And this is the next steps. I think I've covered all this stuff, but the multi-GPU is our next biggest priority. Being able to use the JCUDA is another one. And so we do expect to see some major speedups in the next year. And if you are interested, please get in touch with me. I do have a couple of books to give away. I have stickers. So if you're interested in how to include this in your application, if you're interested in contributing any algorithms, we're very active on the user list, on the dev list. Here are the links that you'll need to know. The homepage is mahout.apache.org. The Apache Git repo is mirrored directly to GitHub, so we can get PRs there, pull them in, we can do comments on them. We have a Google Summer of Code intern this summer doing rewriting canopy clustering, and I think probably bisecting k-means too. So that's the mailing lists, where to download and embed, Maven profile, stuff like that. So thanks very much. Any questions? Questions? Hungry? Thanks a lot.